In a previous video, you met our chickens in our backyard, and our chickens lay eggs of varying sizes. So some actually are quite large, whereas others are quite a bit smaller. And what I thought would be interesting to do would be to categorize how many of each type of egg they get, how many big eggs we get, how many small eggs we get. So today we're talking about what to do with data. How do you collect data and how do you organize it once you've got it? So let's start with this big one. If we have a big egg, we're going to weigh it on my scale here and just see how much it weighs. And it looks like 64.5 is what we get for its weight. And so I'm just going to write that down here on my whiteboard. My small egg, by contrast, is 34.7 is how much it is going to weigh. And so what I'm going to do is I'm going to weigh all these eggs, and I'm going to see how much they weigh, and I'm going to have a bunch of data, and I'm going to try to see how I want to organize it. We're done finally. So I finished counting all of the eggs, and I'm really interested in classifying how many of each size do I have, how many big ones do I have, how many medium-sized ones, and how many small ones I have. So I'm going to organize these into groups, or what we call classes, and we're going to kind of model how you turn a bunch of data like this into nice organized tables and structures so that you can communicate it effectively and make sense of what's going on with all your data. So here are the weights we got when we weighed all of our eggs. And now the question is, what do we do with this? Right now it's just a jumble of numbers. How do we organize this and make sense of it? And what we're going to do at first is we're going to use what's called a frequency table. And that's something that looks a little bit like this. It's a table that has ranges of values on the left and frequencies, or how often our data points fall into that range of the values on the right. These ranges of values on our left are what we refer to as the classes. And each class has both a beginning value and an ending value, and these are called the class boundaries. And if I subtract them from each other, say we do 60 minus 45, we get 15, and 15 would be the class width. And so that's what we refer to as the width of that class. And these two values, the 45 and the 60, are the boundaries or the class limits of the class. And then within each class, it's the frequency. It's like this number 4 tells us how many data points fall within that given range. So that's what a frequency table is, and there's actually lots of ways to make a frequency table. Our textbook and others, I believe, kind of error in the way that they portrayed as there being one correct frequency table for every set of data. The truth is there's lots of different ways to make a frequency table, and it kind of depends upon the scenario and the setting as to some of the nuance. But all good frequency tables share two key principles. The first one is that each class should be roughly the same width. Notice this table follows that pattern. 60 minus 45 is 15. 45 minus 30 is also 15. 30 minus 15 is also 15, and 15 minus 0 is 15. So each class, in this case, is the exact same width. They should all be close to the same. It wouldn't make a lot of sense for one class to be a width of only 2 or 3 units and the other class to be widths of hundreds of units. It would distort your data in the way it looks. And the next important value is that the classes should span all of the data. So if your data values run between numbers between 0 and 60, then it makes sense for your classes to run between 0 and 60. If your data values are only between 45 and 60, then it wouldn't make sense to have these classes here on the bottom. Similarly, if your data values go above 60, you would need extra classes. These two feel kind of common sense to me. And we're going to not worry so much about the particulars of the table, but worry about the common sense, making sure we follow these two principles and that our tables look reasonable and presentable to those who read them. So our first method is to start with the number of classes that we want to create. And so in this case, let's start with just 3 classes. We're going to start with a class for small eggs, a class for medium eggs, and a class for large eggs. Well, if we know we have 3 classes, we need to sit and think, what ranges should I choose for these classes? Well, one of the ways we can do that is to try to find the largest and the smallest values. And if we take the largest minus the smallest values, it gives us what we call the range of our data. And so if we look at that range of the data and then divide that by the number of classes, it will give us a good picture of how big we need each class to be. So as I look at this data, my largest value is the number 68. My smallest value is the number 34.7. So if I take those two numbers, 68.0, and subtract 34.7, I get 33.3. And that is our range of our data. And then if I take 33.3 and divide that by 3, I get 11.1, which is what I want each class width to be. And so that gives me a bit of a basis for how I want to start creating these classes. So my first class is going to start with our smallest value, 34.7, and then it'll add 11.1, and that'll give me my next largest class. So it'll go from 34.7 to 45.8. And then my next class is going to run from 45.8. I'll add 11.1 to that to make this next class, and that'll be 56.9. And then finally, my last class, I'll start with 56.9, and I'll add 11.1 from that, and that gets me 68.0. Notice I've satisfied both of my goals. My classes, I've satisfied all of my goals. My classes are all the same width, and they span the entire range of my data. So if you know how many classes you want, in this case 3, then we can use a simple formula like this to figure out roughly what the class width is, and we can build our classes this way. If you created your table and your classes slightly different, no big deal. We'll have almost the same results. So now what we need to do is place all of our values within our classes. So I'm going to go through each one and look at 64.5, and I'll mark it out. And 64.5, you'll notice, is in this third class. So I'm just going to make a little tick mark. And I'll continue through here with each one, making a tick mark until I fill them all out. So let's speed up and try to do this a lot quicker. There, now that we've got that one done, all that's left is just to count them up, and we can see what our frequency is. So it looks like for this small size, we got a frequency of 11. For our medium size, we had a frequency of 18. And for our large size, it looks like we had a frequency of 21. And this is how we can create our table. Notice I probably should have labeled them all with things like size. I could write class or boundaries here. And then over here, I can put my frequency as we go through and put each frequency down. All right, so this is the first way. The first way to create a table is to start with the number of classes. From each class, you decide how wide the classes need to be, and then you tally them all up and come up with your frequency. However, there's a second way to create a table, and that's to use predetermined widths for each class. And this is really useful when you're dealing with data that you're familiar with. For example, if we were dealing with GPA data, it might make sense to break them down into 1 to 2 and 2 to 3 and 3 to 4, because those are common breaks that everyone's quite familiar with. But when you get numbers like these, where we just have a bunch of eggs, it's not quite clear what the familiar places are to break them down. It turns out that I actually do know that there are places to break them down, and the most natural is to use what people use in grocery stores. So in grocery stores, they have sizes. And so if you ever buy eggs from a grocery store, you'll notice it has a size on the front. And it turns out the extra large eggs run from 63 and up. So those are all the eggs that are greater than 63.8 grams in this case. The large eggs run from 56.7 to 63.8 grams. The medium eggs run from 49.6 up to 56.7. The small eggs run from 42.5 to 49.6 grams. And there is one smaller size. I've never seen them in the grocery store, and they're called peewee eggs. So we'll just put a P for peewee. And peewee eggs are eggs that are less than 42.5 grams. And as we go through, let's fill all these out as well. And what if instead of doing all the effort I did last time, we just magically snap our fingers and our answers will pop into place for us? So here we go. All right, that was easier than counting them all up. So there is one question, and it showed up on the last table, and it shows up on this table as well, and that is, what do you do about a number like this, that's 49.6, that happens to land in both classes? So you'll notice 49.6 is in the small class, and it's also in the medium class because we use them both for that boundary. Well, you could, if you like, rearrange your boundaries so that they don't meet. I tend to like to make them meet, and there's just a general convention, and the general convention is that we always go into the larger class. So if you hit on the boundary, you put that in the larger one and not the smaller one. So now that we have this table figured out, let's see how we could visualize it or represent it in other ways. First, there's one thing that we often do, and often when we have the table, we make one additional column to it. And that is, beyond the frequency, sometimes we use what's called the relative frequency. And relative frequency is just what we get when we use the frequency in percentage terms instead of total terms. So we use a percentage instead of the total. So instead of 5, we're going to take 5 and divide it by 50, which will give us 0.10, or 10%. So we can use 10% for that first relative frequency. And if we go through and convert all of these, you'll notice that this one is 24%, this one is 24%, 32%, and 10%. And as you'll notice, there's no real difference between frequency and relative frequencies, but sometimes relative frequencies communicate better to our audience what is going on with our data. So as you can see, about a fourth of our data runs in the small and medium, and about a third runs in the large, and 80% of our eggs are in this range, small, medium, and large. So once we have our table well established, what we'd really like to do is create a way to visualize these. And the way we're going to visualize these is called a histogram. And a histogram is a graph of these on an XY coordinate. And for a histogram, we start by placing these bounds on the XY axis. So I'm going to place 42.5 on the XY axis, and then I'm going to go through and add all of the other bounds as well onto the XY axis. And you'll notice as we look, we have the same number of gaps, if you look at the gaps between, as we do classes. Now, on the y-axis, we're going to use these frequencies. So notice our largest frequency is the number 16. So we're going to kind of put some tick marks up here that go to 16 or a little bit bigger. So tell you what, I'll put 15 here and I'll kind of scale down. 50. Now what I'm going to do is I'm going to draw myself a box, and for each box I'm going to go the height of the frequency. So my first box represents this first peewee class, and you'll notice that the peewee class is under 42.5, and we had a frequency of 5 of them on there. So that's the box that represents this. My next box is going to represent the small class, and that's going to be between 42.5 and 49.6, and it'll go up to 12. And we'll repeat this for all the rest of our classes. And now that we're done, we have a really good representation of our data. And so if someone looks at this, they can quickly see, oh, look, most of the data is between 42.5 and 63.8, with a few on the outside. And the largest section was the 56.7 to the 63.8 section. A few notes about histograms. We always use these boundaries as our heights, and we put them on the edges of our boxes. We don't center them in the middle of the boxes. And you'll notice we use no gaps as we draw these. The reason we don't want to have gaps is because we really want this histogram to represent every possible value that could show up as we weigh these eggs. You can think of the histograms as kind of a intermediary between data, which could come in lots of values, and a graph, which is continuous and flows across a whole range of values. And so what we're trying to do with the histogram is kind of bridge that gap to go between the two. And as you move towards more and more data, you can make your histograms finer and finer, and they start to get those shapes that look like graphs do. So finally, there are a few histogram shapes that are quite popular and that are worth kind of talking about independently. The first is called mound-shaped symmetrical, and that is what it sounds like. It's a mound shape. Notice the histogram goes up and then comes back down. Notice it goes up and then comes back down. It kind of looks like a mound, and it's symmetrical in that the two sides are fairly similar to each other. The next one is called uniform, and uniform is where all the values are roughly the same height. They never turn out to be actually the exact same height, but they're roughly the same height, and that's called uniform, where every range of values that you have for your data has about the same probability of being selected. Next, we have what's called a skew left graph, and these get confusing because there's also a skew right. And if you just look at this picture, it kind of looks right because notice the data is kind of clumped on the right-hand side. But this is actually skew left, and we'll talk a little bit about why that is, and it might make more sense after we talk a little bit about averages. But you'll notice the center of the data is right here at this highest value. That's where the top of your mound is. But these values on the left here are skewing the data this direction. So if you were to go find the average would actually be less than the top of that mound. And so that's why it's skew left. It has a tail or these extra values on the left-hand side of the data. I'm not going to draw it, but you can imagine a skew right is the exact same picture, but turned towards the other direction. Finally, what's called a bimodal distribution. A bimodal is where you have two different mounds going on. We have a mound here and a mound here. And what a bimodal distribution usually tells us is that there's actually more than one population going on. So, for example, if I took all of my eggs and weighed them and I saw a bimodal distribution, it'd probably tell me that there's two different types of chickens that are laying eggs. One maybe a large breed that weighs large eggs, and another a small breed that lays smaller eggs, and that's why the two mounds show up. So what we probably have is two mound-shaped symmetrical distributions that are a little bit offset. And so bimodal distributions really give us some important information as we go from there. All right, these are just a few of the important histograms that we'll talk about. But when we come back to class next time, we'll talk more about histograms. You'll have some opportunities to make some of your own. And we'll talk a little bit about cumulative distributions and some other ways that we might think about and work with these things. So good luck, and I'll see you in class.